Welcome to your Physics 12 screencast on problem-solving strategies with electrostatic forces. Like we developed earlier in the year, remember, try to avoid having a particular type of question memorized and recognizing it and regurgitating a solution. Instead, think of the common strategy you would use for similar sorts of situations and apply those strategies. And that way every problem really appears the same. So in our study of electrostatic forces, we'll use the same strategies we developed with other vectors, whether we were adding forces or momentums or fields. We broke it into 3 steps. So that was, we made a free body diagram, then we made a vector diagram based on the free body diagram, and then finally we did some calculations involving some physics principles and also some geometry or trigonometry. So we'll model those 3 stages again here, except we'll be applying them to electrostatic forces. Now, as always in problem solving, there are some underpinnings or fundamentals you need to bring to the table, unique to each situation. In this case, we're dealing with electrostatics, so we have to be able to apply Coulomb's law. So shown down here at the bottom, you need to recall that Q stands for the charge, and very often these charges are quite small, so they may be represented in microcoulombs. And remember, micro is 10 to the minus 6. So 1 microcoulomb is 10 to the minus 6 coulombs. The other thing, D stands for the distance between the center of the 2 charges, measured in meters. And third, K stands for Coulomb's constant, which is 9 times 10 to the 9th. So bring that to bear as we're problem solving with electrostatic forces. Other things you may recall from earlier screencasts we've done is that opposite charges attract each other. So here we have a negative 20 microcoulomb charge and a positive 40 microcoulomb charge. They will exert equal and opposite attractive forces on each other. In another screencast we did, you saw situations that similar charges repelled each other. So here we have, for example, a negative 20 microcoulomb charge and a negative 40 microcoulomb charge. These charges will produce an equal and opposite repulsive force between the 2 of them. Similarly, between the 2 positive charges down here, also an equal and opposite repulsive force between the 2. So that will help you determine the direction of the electrostatic force that may be involved in the problems. So, in the back of your mind, as you're approaching these situations, focus on 2 key items. First, pay attention to the direction of the electrostatic force that would be on each charge, just like we've illustrated. And second, do some thinking about how these 2 or 3 forces would compare to each other. What's their relative size? And that might take a little bit more work, but if your free body diagram shows these vectors with appropriate relative sizes, it'll really help your intuition when you continue on in your problem solving. So let's begin. So let's model these problem-solving strategies together, but just before we do, when you're watching a screencast that illustrates problem-solving techniques, to get the most out of them, I would suggest that you pause the video at an appropriate place, work through the solution as best as you can on your own, and then continue with the video to compare your work against an ideal solution. Hopefully you'll learn much more from the process if you follow that. And I'll try to give you obvious indicators about when it would be appropriate to pause the video and then continue on. One other note for you, each of these stages is fairly complex and the explanations will take some time. So I've broken this particular screencast into 3 parts. This first stage will illustrate creating free body diagrams, but the next 2 stages, that is making vector diagrams and the calculations associated with those vector diagrams, will appear in 2 separate screencasts right after this. So decide which one is most useful for you and then watch the appropriate one. All right, here we go. So our problem-solving approach, as we mentioned, is to begin with a free body diagram. And when we do it, we're going to pay particular attention to the direction and the relative size of each force that we put in the diagram. So the situation we'll work with first will be a one-dimensional situation where we've got 3 charges presented to us. So we have a 20 microcoulomb charge, a negative 10 microcoulomb charge, and a 50 microcoulomb charge. And in case it's hard to read on the screen, the first 2 charges are separated by 2.5 meters, and the 2 charges on the right are separated by 3.5 meters. So use that information and try to draw a free body diagram showing the forces that should be on each of the 3 charges. And just a hint, there should be 2 forces on each charge. So give it a shot, and then we'll pull ourselves together and see how you made out. So welcome back. Let's take a look at the solution. So first, if we consider the positive 20 microcoulomb charge and the positive 50 microcoulomb charge, they're both positive charges, so they would produce a repulsive force between the two of them. So the 50 microcoulomb charge would be pushed to the right. I've chosen just an arbitrary length of the force vector here drawn in blue, and I would need to draw the same length of vector on the left, showing the repulsive force on the 20 microcoulomb charge. Now let's consider the negative 10 microcoulomb charge and the positive 50. They're oppositely charged, so they're going to attract each other. So there's going to be a force to the left. But before we go on, how should the length of this force vector compare to the blue vector that we drew? Should they be the same size, larger or smaller? So we have to do a little bit of digging here. So first, recall that the electrostatic force is directly proportional to the product of the two charges. So let's look at the two situations to see what we were faced with. So first, we had a 20 microcoulomb charge repelling a 50 microcoulomb charge. I'll leave the subscripts off for the moment. And then in the second case, we had a 10 microcoulomb charge. Yes, it was negative, but that just changed the direction. We're interested just in the magnitude of the charge here. So that 10 microcoulomb charge was attracted to the 50 microcoulomb charge. So if we look at these two situations to compare them to each other, then really all we did was decrease the overall charge by a factor of 2, going from the 20 down to the 10. That means we would expect that the electric force in the second situation should be 2 times smaller than in the first situation. So that uses Coulomb's law in considering the impact of charge. But that's not all. We also have to consider the impact of the distance between the two situations. So let's repeat that process. So the electric force is inversely proportional to 1 over the square of the distance. So if we look at the two situations, in the first case, the 20 and the 50 microcoulomb charge were separated by 6 meters. And then we switched to the other situation, the 10 microcoulomb charge. It was only 3.5 meters away. So in other words, the distance decreased by a factor of about 1.7 times. But because the electrostatic force is inversely proportional to the square of the distance, we need to look at the impact that would be on the square of d. So if we square 1.7, we'll get 2.9. Now remember, there's an inverse relationship between force and distance squared. So if the distance squared got smaller by a factor of 2.9, then the electrostatic force should get larger by a factor of about 2.9 times. So what we need to do then is compare these two final situations. Due to the charge, our second scenario should be 2 times weaker, but due to the impact of the distance, our second scenario should be almost 3 times larger. In other words, we can see combining these two effects that the second vector should be larger than the first vector. Not a lot, but larger for sure. So that's the logic or rationale that you would exercise behind the scenes as you're creating your free body diagram, and will really help your intuition as you problem solve. So when you compare the green vector that we've got here to the blue vector, you can clearly see it is longer. So the 50 microcoulomb charge would be attracted to the left towards the negative 10 microcoulomb charge, and there would be an equal and opposite attractive force between the negative 10 microcoulomb charge and the positive 50 on the right. So the last situation we have to consider is the force between the negative 10 microcoulomb charge and the positive 20. They're also oppositely charged, so there would be an attractive force on the negative 10 towards the positive 20 microcoulomb charge. And again, these would be an action and reaction pair. To determine the appropriate length of these two vectors, we'd have to go through the same exercise we just did with the blue and green vectors. But we'll leave that part for the moment. So in essence here, this is our free body diagram. This is the first stage of what we'd work through. Hopefully this matched your solution that you had or very similar to it. So if you've learned from that process, we should now be able to exercise this in a little more challenging situation. Rather than one-dimensional, this is now a two-dimensional scenario. So just to help you read, in case you're looking at this a little small on your cell phone, we've got 3 charges, a positive 40 microcoulomb charge. That's 4 meters away from a negative 10 microcoulomb charge, which is 3 meters away from a 30 microcoulomb charge. And by the Pythagorean triangle, the 40 and the 30 microcoulomb charge are 5 meters apart. So now repeat the exercise that you've just had illustrated. Try to create a free body diagram showing showing the forces acting on each of these 3 charges. And again, the hint, there should be 2 vectors in each situation. Think carefully about their direction and how long each vector should be compared to one another. So this would be a good place to pause the video and then restart once you have your free body diagram done. Okay, welcome back. Let's see how you did. So first, we'll consider the positive 30 microcoulomb charge and the positive 40 microcoulomb charge. They are both positive charges, so they should repel each other. And again, I'll draw a vector just with an arbitrary length that is showing the repulsive force. I need to draw an equal length vector in the opposite direction on the positive 40 microcoulomb charge. So that's my starting reference length of vector my others must compare to. So now let's look at the positive 30 compared to the negative 10. They're oppositely charged, so they should attract each other. So the positive 30 microcoulomb charge would experience a force directly upwards. Now again, same problem. How long should this vector compare to the last one that we just drew? So let's take a look at that situation, and again, it'll take a little bit more work, but let's see what we can figure out. So first, if we look at the impact of the electric force on the product of the 2 charges involved. So in the first scenario, we had a 40 microcoulomb charge that was repelling a 30 microcoulomb charge. And in the second scenario, we had a 10 microcoulomb charge, again I'm ignoring the minus sign, also impacting the 30 microcoulomb charge. So if I look at the effect between these two, the main effect was to decrease the size of the charge by a factor of 4 times. So therefore, we would expect that the electric force should be 4 times smaller in the second scenario. And like before, we need to also consider what's the impact of the distance on these 2 forces. So in the first situation, we'll look at the electric force, and remember it is inversely proportional to the square of the distance. So in the first scenario, they were separated by 5 meters. And in the second situation, they were separated by 3 meters. So that distance decreased by a factor of 1.7. Now again, for electric force is inversely proportional to 1 over the square of the distance. So we need to look at the impact on the square of this change in the distance. So if we square that, we're going to get 2.9. So that means we would expect the distance squared term to get 2.9 times smaller, which means the electric force should get 2.9 times larger. So we need to compare these 2 scenarios to each other. So due to the distance, the electric force should be almost 3 times bigger, but due to the charges, it should be 4 times smaller. So if we look at those 2 scenarios, clearly overall, that force vector should be smaller than the first one that I drew. So a lot of reasoning behind it, but again, it really helps your intuition if you work through that. So if we compare that green vector to the blue vector, you can see it is quite a bit shorter. So that matches the logic of what we just developed. That attractive force is on both particles, so the 10 microcoulomb charge will be pulled downwards towards the positive 30. Next scenario, we'll compare the negative 10 to the positive 40 microcoulomb charge. They are oppositely charged, so again there would be an attractive force between the 2 of them. So the negative 10 microcoulomb charge would be pulled to the left. And again, now we need to think of how long this force vector would compare to the last one that we drew. So we'll go through the same exercise and see how they compare. So, due to the charges, the electric force directly proportional to the product of the 2 charges. So in our last scenario that we had a 10 microcoulomb charge that was attracted towards the 30 microcoulomb charge. And in our new scenario, we now have that 10 microcoulomb charge attracted to a 40 microcoulomb charge. So there has been an increase between these 2. The increase from 30 to 40 would be an increase of about 1.3 times larger. So that means we would expect the electric force to be about 1.3 times bigger than it was before if we only considered the impact of the size of the charges. All right, so second option, as we did before, we need to look at the impact of the electric force on the distance change between the two. So electric force is inversely proportional to the square of the distance. So in the first scenario, the two charges were 3.0 meters apart. And then in the second scenario, they were 4.0 meters apart. So we had an increase, again, of about 1.3 times in the increase in our distance. But remember, this is related to 1 over d squared, so we need to look at the impact on the square of the distance. So if I square 1.3, we get about 1.8. So in other words, d squared will increase by about 1.8. Therefore, the electric force will be about 1.8 times smaller due to the impact of the change in distance between the charges. So if we compare those two scenarios overall, we have an increase of 1.3 due to the difference in charges and a decrease of 1.8 due to the change in distances. And we can see this second scenario is going to be the overwhelming one. So overall, this new vector that we draw, the red one, should be smaller, slightly smaller, than the green one that we just drew. So if you take a look, as we draw our green vector right next to it, you can see the red one is slightly smaller than the green one, so that matches the logic that we've just worked through in our free body diagram. And remember, these are equal and opposite pairs of forces, so the 40 microcoulomb charge would be pulled towards the right, it would be attracted towards the negative 10 microcoulomb charge. So now we have a pretty complicated free body diagram that completes the first stage of problem solving with electrostatic forces. All right, on to stage 2. Stage 2 in the problem solving, where we create a vector diagram based on the free body diagrams that you just learned how to make, will be in the next sequence in this series. So exit this video, and if you're interested, continue on with the next stage.